gauge that are charged under the standard model gauge symmetries. And so when SUSY gets broken in this sector, the messengers through 1 and 2 loop diagrams, they transmit the breaking to the supersymmetric standard model. And in this scenario, if you have a low scale of supersymmetry breaking and it's only broken in this sector, it turns out the gravitino is very light. Ignore this F0 over F factor for a moment and just look at the rest of the formula. This formula is saying that the gravitino mass would be 24 keV at that SUSY breaking scale, which is it's kind of problematic. It's more like a warm dark matter candidate. But you can crank this up if you imagine that there are other SUSY breaking sectors that transmit or that couple to the standard model only gravitationally. And those other sectors could have a much higher scale of supersymmetry breaking. And so that's what this factor F0 over F is doing. It's saying that we could use that idea to push the gravitino mass higher to higher values. But it turns out you can't do that indefinitely, because you see, one of the nice things, one of the reasons people like gauge-mediated supersymmetry breaking is that it naturally solves the flavor problems of supersymmetries. It suppresses flavor-changing neutral currents, whereas gravity mediation has that problem. And so if you have too big a ratio here, then you get too much gravity mediation in the mix, which is pushing these flavor-changing neutral currents to unacceptable values. So that correlation puts an upper limit on the gravitino mass. Okay, so that's point number one.
Sorry,
yes.
Just a quick question.
Yes.
So, but in gravity mediation, you can of course solve that problem by just postulating that things are flavor diagonal. So you can just do that in this setup as well if you wished, right? So it's not an absolute.
Yeah, I guess. Yeah, I'm not an expert on these things, but so I'm not sure if there's an argument against what you just said, but yeah, I suppose you can impose it by hand.
Okay, thanks.
Yeah, sorry, I'm not an expert at all on supersymmetry. That's why we hired we recruited Stuart Robbie to be on our collaboration. He was the person who was helping us with a lot of the SUSY details. Anyway, so let me get onto this gravitino overproduction problem. The famous problem is that gluon fusion in the early universe into gluinos and gravitinos will tend to overproduce the gravitinos if the reheat temperature is high enough in inflation. And here we need the reheat temperature to be at least the SUSY breaking scale to have this phase transition happen in the first place. So we're going to assume that it's this minimal value that gives you the maximal parameter space to make this all work. And so this graph from the Craig et al. Paper is showing the SUSY breaking scale versus the gravitino mass. It has these contours of these are the contours showing you when you get the right relic density of gravitinos for a given gluino mass. Okay, and so you see as you push the gluino mass higher, these contours move down, and this region is ruled out by gravitino overproduction because the LHC puts limits. The gluino mass is actually, it's already greater than about 2 TeV. This M3, this is what do you call that? It's not the physical gluino mass, but it's the parameter.
The soft mass.
The soft mass, thank you. So yeah, there's a little bit of leeway between this parameter and the actual gluino mass. Okay, so that's what these curves are. And so these green lines are telling you we're already limited because there's a correlation between the neutrino mass and the scale of SUSY-breaking. And so the current limit from LHC is saying that we have to be above this green line, whereas eventually a future circular collider will be able to probe neutrino masses up to this green line. So we know we're in this region, and we also know there's a limit from Big Bang nucleosynthesis from Higgsino decaying into gravitinos and hadrons. So that excludes this whole region. And you're left with just this little triangle. And you see this is in the tens of TeV range. And so that's another motivation for this 10 TeV scale. And now I'm just going to show you one more slide, because one of the difficult things was just to come up with a model. You see, Craig et al., they had a basic framework, but they didn't have a concrete model. And we wanted to have a concrete model because we thought maybe we could get some interesting correlation between leptogenesis and gravity waves instead of baryogenesis, since we don't have electroweak baryogenesis. So we wanted to have a model that explained neutrino masses and would give us leptogenesis in addition to gravity waves. And so I'm just going to tell you the basics of this model that we came up with. There's this field X, that's the thing that gets the VEV in the phase transition. So that's breaking supersymmetry. And then there are these superfields phi and phi prime called O'Rafferty fields. And those are the things, when you integrate them out, they produce the one loop potential, the potential for X. And then here are the messenger fields. There's 4 sets of them as well. Those are the things that transmit SUSY-breaking. And then when we introduced some heavy right-handed neutrinos, it turned out we needed 2 kinds. And finally, you have the standard model fields that are relevant to our study, the lepton and the up-like Higgs. So those are the ingredients of the model. And well, they have some R charges in supersymmetry. They also have there's a U1 that we add in the hidden sector, which gives rise to a D-term potential, and that helps to give a strong phase transition. And then there's some SU5 symmetry, which you can think of as being either grand unification of the standard model gauge group or just an approximate global SU5 into which we embed the standard model gauge structure. And so these messenger fields are carrying standard model quantum numbers accordingly. And then there's the SU2 and there's the U1Y of the standard model. There's the lepton number. There's some discrete remnant of lepton number that's unbroken. We have to break lepton number in order to give neutrino masses, but then there's a discrete symmetry left over, which helps us to simplify the Lagrangian. And okay, so those are the basic ingredients of the model. And to understand how to put them together into potential, it turns out there's a nice thing you can do. You can pair up these O'Rafferty fields with the messenger fields into 6 component fields, called them psi. And then the model looks extremely simple. The superpotential just has these 4 terms that couple the X field to the psi fields. And this is all you need to get the supersymmetry breaking, this plus the D-term potential. That's what you need to generate this SUSY-breaking potential for the modulus field.
Sorry,
so it's, yes.
I'm sorry for another interruption. I just had one. I was trying to work out what the asterisk means for the 5-plets, but I guess that's because
Yes.
under SU5.
Yeah, what it means is that so think of these as being like fundamentals of SU5, and so the top 3 components carry SU3 color. The bottom 2 components carry SU2 left. So the star just means that the bottom components are charged.
Yes.
Yeah.
Okay.
Thanks for the question. Okay, so then the other part is the part that deals with neutrinos, and that's also pretty simple too. And it also couples to the X field. So you see the heavy neutrinos are going to get some mass in this phase transition. And that's how we were hoping to link leptogenesis to the phase transition through this coupling. And the rest are kind of standard things that you would write down to generate neutrino mass. But it turns out it's not quite standard because we needed two kinds, N and N prime, and JS is going to explain all of that. So that completes my little introduction, sets the stage. Maybe I'll just pause to see if there are any other questions before I turn it over to Benoit. Okay, so I will stop sharing and
Okay, hi, can you see that?
Yep, we can see it. Thanks.
Yeah.
Okay, so thank you, Jim, for the introduction, and thank you, Peter, of course, for inviting us. So yes, like Jim said at the beginning, we'll be talking more specifically on two kind of cosmological signal that this SUSY-breaking phase transition can produce, which are gravitational waves as well as primordial black holes. And something special about these two signals is that they really need the phase transition to be first order to be able to be produced, simply because first order phase transition in the early universe will happen through bubble nucleation. So they start in small bubble where the true vacuum nucleates, and these bubbles expand until they fill the whole universe. And that's with these bubbles that we will be able to produce gravitational waves as well as primordial black holes. So I will begin with gravitational waves. So here, just to introduce how we can produce those waves, I show some picture of a simulation made in this paper here, which shows essentially the energy density in the plasma at different stages during the phase transition. So we see at the beginning, we only have a couple of isolated bubbles that are slowly expanding in the plasma. And at that stage, it's still impossible to generate gravitational waves simply because each of these bubbles have a spherical symmetry. So in order to produce waves, we need to break that spherical symmetry, which will happen a bit later during the phase transition when all these bubbles collide with one another. So this is what happened in the second picture here. So basically here the whole universe is filled by the true vacuum, and we have something that is much more chaotic and can actually produce gravitational waves. So we know a couple of mechanisms with which we can produce gravitational wave with the first order phase transition, but it is believed that the dominant one is through sound waves in the plasma, at least for this SUSY-breaking phase transition. So basically what happens is that these bubbles collide, and by colliding, they produce sound waves in the plasma, as we can see in the last picture. And slowly these sound waves will be converted into gravitational wave that we can hope to observe at some point with some detector. So now that we have some basic mechanism with which we can produce gravitational waves, we want to make an actual prediction. We want to see how well our SUSY-breaking phase transition can produce those waves. And fortunately, there has been a lot of paper on that subject. People have made a lot of simulation to be able to have a good idea of what kind of gravitational wave spectrum can be produced by a first order phase transition. And this is a fit from one of the simulation here. So basically we want to predict this omega function, which is the spectrum of gravitational waves. And we can, you can see that it can be factored in terms of different terms. So on the right-hand side completely, we have some function phi, which parameterizes the shape of the spectrum. and this is basically fitted from the simulation. It's simply a broken power law. Then we have this fraction here, which tells us how much of the energy release in the phase transition will be converted into sound waves in the plasma. So it depends on a couple of factors like the Hubble rate and the mean radius of the bubbles, and this K, which is the amount of kinetic energy which will be produced. Then we have this omega tilde, which is the fraction of these sound waves which will be converted in gravitational waves, and this is purely a number which is determined from simulations. Then we have some factor to take into account the redshift of those waves. And finally, this numerical factor, which is just to get this normalization here that we want. And here on the bottom figure, I show some typical gravitational wave spectrum that we can produce with these black line here, as well as the sensitivity curves of a couple of experiments. So yes, now that we have a way to predict a gravitational wave spectrum, it's not enough just to have that. We need to actually to detect this spectrum. So to do that, we need to compare it to some experiment and to compute this signal to noise ratio that we can hope to observe with some experiment. So this is given by this formula here, which depends on three quantities. This T, which is the duration of the mission. Typically, it's supposed to last a couple of years. For example, in the LISA experiment, which is supposed to be launched, I think, in 2034 or something like that, it's expected to last 4 years. Of course, it also depends on the spectrum of wave produced and on the sensitivity curve of the detector. And this is really something that should be provided by the experimentalist, something that depends on a lot of different factors like the type of detector and its configuration. And then once we have this signal to noise ratio, so this gives us simply a number, and if this number is larger than some threshold, we can conclude that we would be able to observe that signal. So again, this threshold can depend on a lot of different factors, but usually it's around 10. For example, for LISA, it's expected to be 10, this threshold. Okay, so now we really have a way to determine if we would see some gravitational wave produced by this SUSY-breaking phase transition. So to explore how well our model can produce these gravitational waves, I made 2 scans of the parameter space. In both scans, I vary this lambda parameter, which I remind you is the coupling between the pseudo-modulus field and these messenger fields. And this essentially controls the potential barrier between the false and true vacuums. And then on the left-hand side, I also vary this ratio D over F, which were the 2 SUSY-breaking scales that we needed in our model to make a first-order phase transition. And this will control the strength of the phase transition. And so here I show these dashed line here. So whenever we are below these line, these are models that we would be able to observe with each of these detectors. So we see that there is quite a large region in the parameter space that would be probed by at least one of these detectors. CE here is the Cosmic Explorer, which is an Earth-based detector which has been proposed. And we see here that it's the most sensitive to those waves. And on the right-hand side, here instead of varying D over F, I vary this G U1 decoupling, which essentially controls the web of the pseudo-modulus field. And again, we can find quite a large region in the parameter space where some of these experiments would be able to probe those waves. So yes, again, here I show some example of a spectrum that we can produce with the sensitivity curve of each of these detectors. And here, the sensitivity curve are normalized in such a way that whenever we have a spectrum that peaks above that curve, we would be able to observe it with that detector. So we really only care about the maximum of these curves. So here on the right-hand side, I only show the position of that maximum for all the points that I sampled to make those scans. And we see why the Cosmic Explorer and Einstein telescopes seem to be more sensitive to those waves. It's not necessarily because they are more sensitive than the space-based telescope like LISA, EDGE, the Saigon Bibio. It's simply because their frequency range is much closer to the frequency that we produce with our phase transition. And the reason for that is just because it happens at the PEV scale. So the peak frequency is essentially proportional to the temperature at which the phase transition happens. So because it happens at a higher temperature, though the frequency range is also higher than for example, the electroweak phase transition. So that's why really the best kind of experiment to probe those waves are Earth-based telescopes like CE and ET. Okay, so I think it's quite a nice result to see that we can produce quite a lot of gravitational wave and can probe quite a large region of the parameter space. So now I wanted to talk more about something that is a bit newer, which is the production of primordial black holes. So yes, unlike gravitational waves, the production of that kind of object is still very early, in meaning that it hasn't been studied a lot yet. So there's still a lot of work to do to really fully understand how they are produced and what will be the spectrum of black holes that will be produced during a first order phase transition. So here we really only wanted to give some argument to say that this is something that we should take seriously and that could really happen and would require more work to really understand completely. So there have been a couple of mechanisms proposed to produce these black holes during a first order phase transition. Here what we will consider is what we call the mass gain mechanism. So basically this can be used whenever we have a particle in the plasma which acquires a very large mass during the phase transition. So before the phase transition in the false vacuum, it needs to be quite light so that it is present in large quantity. But in the true vacuum, it should be very massive in such a way that it is much more massive than the typical kinetic energy of these particles before the phase transition. If this happens, then these particles will simply not have enough kinetic energy to enter the bubble wall, so they will always be reflected in front of the wall when they collide with it. And they will essentially be trapped in the false vacuum in that case. So what will happen is something shown in this picture here. So at the beginning, we have the nucleation of this true vacuum bubble shown in blue here. And of course, they are expanding, and at some point they collide and fill most of the universe. But there are these small pockets of false vacuum that are remaining, and these particles are trapped inside of these pockets. And eventually, they will form these bubbles of false vacuum that we can call anti-bubbles. And these bubbles are shrinking. And yes, if the phase transition is strong enough, the density will increase until they can collapse to form a black hole. So that's the basic idea behind the mass gain mechanism. And it turns out that it's actually quite natural to apply this mechanism to our SUSY-breaking model, simply because we have a scalar field, the pseudomodulus here, which acquires a very large VEV in the phase transition. So we will naturally have quite a large variation of masses between the two phases. So as a concrete example, we can take these messenger fields. So before the phase transition, they all have a mass equal to this M parameter, which is simply a parameter and the superpotential. But after the phase transition, when the X field gets a VEV, half of them will acquire a very large mass proportional to the VEV of this field, and the other half will become essentially massless. So with the first half, we will be able to realize the mass gain mechanism and produce black holes. So that's the qualitative idea behind this mechanism. Now let's go a bit more quantitative. So in order to produce a black hole, we want to satisfy the Schwarzschild criteria, which is simply that we want the radius of this anti-bubble to become smaller than the Schwarzschild radius, which is proportional to the total energy inside of this anti-bubble. So to analyze this criteria, we will assume that the anti-bubble is spherical. So of course, this is an approximation. In reality, it will have a more complex shape as shown here. But we can imagine that at late time, surface tension will make it more and more spherical, so it will become eventually a good approximation. We will also assume that the wall is slowly moving and that the total number of particles in the anti-bubble remain constant. And in that case, we can show that the total energy inside the anti-bubble will grow as 1 over the radius. So essentially, you can imagine that each time a particle hit the wall, some of the energy in the wall will be transferred to that particle, and this will slowly increase the total amount of energy in that anti-bubble. So with that scaling relation, we can show that the Schwarzschild radius can be expressed in terms of this ratio of effective number of degrees of freedom in the messenger that contributes to the collapse into black holes, to the total number in the plasma. And it also depends on this ratio of this initial anti-bubble radius squared, in fact. So for example, if we have an initial anti-bubble of the size of the Hubble radius, then this anti-bubble only has to shrink by a factor of 2.8 roughly to satisfy the Schwarzschild criteria. So this might seem like a small factor, but it's not guaranteed that this can happen actually, simply because inside this anti-bubble, there will be some thermal pressure that can slow down the collapse and completely stop it if it's large enough. So this thermal pressure will rise as 1 over the radius to the 4th. And on the other side of the equation, we have the vacuum pressure, which is the main force that drives a collapse, which is a constant. It's simply the difference of potential between the false and true vacuum. And then we also have this gravitational pressure, which will grow as 1 over the radius to the 6th. So it will be only effective when the anti-bubble become very small. And if we want to produce a black hole, we want this total pressure, so the sum of these 3 contributions, to always remain positive whenever the radius is larger than the Schwarzschild radius. And we can show that the maximal constraint will happen only 16% above the Schwarzschild radius. And at that point, the constraint can be written like this here, in terms of this alpha parameter, which here I define as this delta V, so the amount of energy released during the phase transition divided by the radiation energy density in the plasma before the phase transition. So alpha is very often used to describe the strength of the phase transition. So the larger alpha is, the more energy will be released. So we see that here, to produce black hole, we need alpha to be quite large, simply because this vacuum pressure will be larger in that case. Also, we see that it depends on the initial size of the bubble, and it strongly favors very large initial bubbles if we want to produce black holes, because there is more energy stored inside, and it will be easier to reach the Schwarzschild criteria in that case. So again, here I can show some result for the 2 scans that I showed you earlier. So here, just to simplify things, again, we will assume that R0 is roughly the size of the Hubble radius. In that case, the constraint is simply that alpha must be greater than 0.3. And here, these dashed lines show the value of this alpha. And we see that there is, again, some part of the parameter space where alpha is larger than 0.3. So we would be able to produce those gravitational wave, not gravitational waves, sorry, but black holes in some part of the parameter space. So, of course, it's not the whole picture. A more complete treatment should really compute R0 by doing a simulation. And in fact, because it's a stochastic process, this bubble nucleation, we will have a whole spectrum of R0. So to be able to really determine the final spectrum of black holes that would be produced, we will need to do this simulation to determine how large is R0 and what is its spectrum actually. But this was beyond the scope of this study. Here we just wanted to give some argument to say that this is really something that we should take seriously and put more work into in the future. So yes, that's pretty much what I wanted to talk about in my part. So now I will let Jean-Samuel tell you more about leptogenesis. So yes, go ahead, Jean-Samuel.
Thank you. Unless there were questions for Benoit first, maybe
Oh yeah,
I
sure.
can ask now before I set up my screen.
I think you can share. Okay, I think
Can
we
you see
will
my screen?
put the questions at the end then. Yes,
Sure.
you can see your screen. Please go ahead.
So thank you, Benoit. Thank you, Jim. I will try to quickly describe how our model achieves leptogenesis at the PeV scale, so slightly lower than the scale of SUSY-breaking here. So this here is the superpotential that's relevant for leptogenesis. Like Jim mentioned, we need two types of sterile neutrinos, so two types of field, which I call N and N prime. And the reason for that is because with only one type of sterile neutrinos, the vacuum of this theory would not break SUSY. So in order to have a non-vanishing potential in the vacuum of this theory, we needed two types of fields, so N and N prime, which each of them has with different flavors, at least two. And then we couple these two neutrino fields to the SUSY-breaking field X, to this coupling here, and to the standard model Higgs and charged lepton doublets here. So that way we can relate leptogenesis with SUSY-breaking through this term lambda prime X. So to achieve leptogenesis, we need at least two flavors each for N and N prime. The minimum is two, and we decided to work with this minimal case, in which case one of the standard model neutrinos will be massless exactly. And then we can follow two different paradigms, either the normal hierarchy paradigm, which is in which case M1 is the massless neutrino, or the inverted hierarchy, in which case M3 is the massless neutrino. We also made another assumption to simplify our analysis, which is the assumption of minimal flavor violation. In other words, this means that we assume that there is an SO2 flavor symmetry in our model. So the coupling lambda prime here and the mass are universal. Actually, we can split the mass into two parts, a symmetric part and an anti-symmetric part. The anti-symmetric part here is important because it leads to a small mass splitting between the two flavors in our model. And if this mass splitting is very tiny, as I will show later, it will lead to a resonant mixing of the two flavors at the one level. And this resonant mixing is going to be important to enhance the CPA symmetry in our model. So under the MFV hypothesis, minimal flavor violation, all of the flavor violating effects are included in the Yukawa couplings only. So everything else is universal, and the only difference between flavors is put into the Yukawa couplings to simplify our analysis. I forgot to mention, but so we will assume here for simplicity that the mass splitting between the flavors is going to be about one part in, so this is 10 million. So a very, very almost degenerate flavors here, but not exactly degenerate. Now let's take a look at the spectrum for our sterile neutrinos during the phase transition. So before the field X gets a VEV, all of the fields, so both the neutrinos and their SUSY partners, the neutrinos, scalar fields, they all have a mass of about n. They're all nearly degenerate. And then because of this coupling here, as you can see, like Jim mentioned, when X gets a VEV, this term becomes like a large Majorana mass. And so just like in a seesaw mechanism, there's going to be a huge mass splitting between the states n and n prime. So the states n will have a mass which I call mu, which is this combination here, lambda prime times the VEV of the field X. And so these states will become very heavy. They will decay almost instantly, and they will have no impact on leptogenesis, but they will have an impact for the mass generation mechanism for the standard model neutrinos. So they are still important in our model. They are responsible for inducing the light neutrino masses. And then the other fields, n prime, their mass is going to be m times this suppression factor here, m over mu. So here we're assuming that mu is very large. So this is a small number that suppresses the my screen here. That suppresses the mass of these light states here n prime. So n prime will quickly thermalize after the phase transition, but eventually when the temperature drops below their mass scale, so below the scale m squared over mu, this is the scale of leptogenesis. When they decay, they will lead to a lepton asymmetry and eventually the baryon asymmetry in the universe. And so it turns out that we can actually put a bound on the scale m squared over mu, the scale of leptogenesis, using the lower bound on the gluino mass scale. And so this bound is about 500 PeV. So everything in our model seems to point at the PeV scale. This is the most tolerant scale for our model. I will describe a little bit more how neutrinos acquire their mass in our model, because it's not straightforward. So this here is the mass matrix after the electroweak phase transition. So we have nu, which is the standard model neutrinos, the light neutrinos, and then n prime and n are the two heavy sterile fields. We have two different Dirac mass terms. One comes from the Higgs VEV, the other one here comes from the superpotential. And then we have the Majorana mass term here, mu, which comes from the SUSY-breaking term. However, when we diagonalize this matrix here, it turns out that the standard model neutrinos are exactly massless. So at true level, we do not generate a mass for the neutrinos, so that doesn't work. However, when we go to the one loop order, the first loop order, then we have these two diagrams here, which come from a Z boson loop, and then its superpartner counterpart, the Zeno loop here. And with these two loop diagrams, then we can generate a Majorana mass term for the standard model neutrinos nu. And then as you can see here, in the loop diagrams, only the heavy states n are present. The n prime fields are not present. And so because of that, the final mass here is suppressed by this factor of 1 over mu here. So we naturally get a very small neutrino mass because only the heavy states n enters the loop diagram, not the, let's say, the intermediate state n prime. So not only is the mass suppressed by the factor of 1 over mu, it's also suppressed by additional factors coming from the gauge couplings here, and also some loop numerical factors coming from the loop integrals. So overall, this leads to a naturally small neutrino mass without having very tiny Yukawa coupling. So we can estimate actually the size of the Yukawa couplings that we need to get the right neutrino mass here. And as you can see, we need a coupling of about 10 to the minus 6 for the square of the matrix here, y transpose y. So with this Yukawa coupling, we can get a mass of about 0.05 eV. And with that, we can then study what happens during leptogenesis. So very quickly, because this is going to be important for my analysis, I want to introduce the Casasibara parameterization for the Yukawa couplings. Sorry, I'm just going to take water. So this is a parameterization that introduces three matrices, so R, D, and U. So it's a way to relate the Yukawa couplings to the observables for neutrinos. So D here is related to the mass eigenvalues of the standard model neutrinos. U is the PMNS matrix, so everything that is related to neutrino oscillations. And then there's R. R is this matrix here. It's a rotation matrix with a complex angle rho. So rho has a real part A and then an imaginary part B. So we don't often hear about R because it's very hard to constrain it. It's not involved in neutrino oscillations at all. And so we don't hear about it often. But for leptogenesis, it's very important to consider R because the combination that we're interested in is actually this combination here, Y dagger. And as you can see, it only depends on the matrix R and the matrix D. So the PMNS matrix actually vanishes from this combination. So at the end of the day, leptogenesis will depend on only three things: the scale mu, the masses of the two light neutrinos here, M2 and M3, or M1 and M2, and these two parameters here, A and B, which I show here in blue and in green. So A, B, the two masses, and mu, they will fix the Yukawa couplings in our model. So as you can see here, this is a complex matrix, and the off-diagonal term here has a complex phase, and this phase is actually what was going to lead to CP violation in our model. So it involves mixing between the two flavors of sterile neutrinos. It's the only phase that's relevant for leptogenesis. So here I'm showing the decays of N prime, so the intermediate sterile neutrinos, the lightest sterile neutrinos, at the one loop level. So at the one loop level, as you can see, there's a mixing between the two flavors I and J, and so this mixing will involve this off-diagonal term here, which has a complex phase, and so it's going to violate CP, like I mentioned. And now remember that I mentioned that the two flavors were nearly degenerate. So because of that, there's a very tiny mass splitting between them, and this mixing is going to be resonant. And so at the end of the day, this small mass splitting here, delta m squared, which is about 1 part in 1 million here, is going to enhance the CP asymmetry in our model. So it's very important to have nearly degenerate states to enhance the CP asymmetry in our model. So epsilon here is this CP asymmetry that I mentioned. So it describes how the neutrino N prime decays into either particle, is more likely to decay into particles instead of entire particles, because N prime violates the lepton number in its decays. And then we now also have defined the CP asymmetry for the scalar fields of these neutrinos, which is a similar definition. When we compute the CP asymmetries, we find equal expressions for neutrinos and neutrinos, and we get these expressions here. And although it looks very complex, it's actually very simple. So here, we have two fractions. The first fraction here is a ratio of Yukawa couplings. So y dagger squared over y dagger over y dagger. So it's just Yukawa couplings. And this ratio could be as large as 1 because it's just Yukawa couplings. And then on the right, we have a ratio that involves m times the decay rate, and then the mass splitting delta n squared. And this fraction can also be close to 1 if m gamma and delta n squared are of equal size. So all in all, this asymmetry can be as big as 1 in some models. This is what we call resonant leptogenesis. It's when the CP asymmetry is maximal, close to 1. And so all of the neutrinos decay into particles instead of entire particles, and the asymmetry is optimal. However, in our model, m gamma and delta m squared are not close to each other. Actually, m gamma is very small, so we don't have the full resonance that we could have had. But at least we have some quasi-resonant effect. And even in our model, even if m gamma is small, we can achieve some asymmetry of order 10 to the minus 3. So that is going to be big enough, thankfully, to achieve leptogenesis. And here I just want to show that the CP symmetry is going to depend on the mass splitting here. M squared over mu is the scale of leptogenesis, and on the matrix M, which is just how I parameterized the equal coupling here earlier. So just a few parameters will fix the CP symmetry in our model. So it's not enough to compute how many, well, the CP symmetry. We also have to consider any washout effects. So for instance, inverse decays, they will tend to erase any lepton asymmetry that we produce in the decays. So we have to consider the washout parameter. The washout parameter is K. It's just the ratio of the decay rate over the Hubble parameter. And it indicates how much a particle will be in or out of equilibrium when it decays. And it also tells us how much washout there will be in a model. In our case, K is about 1000 when we plug the parameters of our model. And so when K is bigger than 1, we are in the large washout regime. So here it's about 1000. It's a very, it's an extreme washout regime. So there's a lot of washout, which is typically a bad thing because washout will tend to suppress the final lepton asymmetry. But it also comes with a few benefits. So for instance, there are some approximations that we can make to simplify our analysis. I'm not going to mention all of them, but just there are some approximations that we can make. So it's not all bad for us. So to really know what happens at the end of the day, we have to solve the full Boltzmann's equations here to compute the lepton abundance. When we do that, we also have to consider the Svaley-Rand conversion rate, because even though we created lepton asymmetry, Svaley-Rand will partly convert that asymmetry into a baryon asymmetry, because we want to generate a baryon asymmetry at the end of the day. So numerically, we find that the lepton abundance only scales like 1 over k. So even though we have a very large washout here in our model, the suppression effect is not that problematic. So we can still manage to get a sensible asymmetry despite the large washout. And then we can compare with the experimental values obtained by BBN and CMB, so about 8 times 10 to the minus 11. On the left plot here, I showed the evolution of the neutrino abundance and as well as the baryon asymmetry. So this is a typical plot for a large washout evolution. And on the right, I show so the baryon abundance that we get for varying values of K, the washout, and varying CP symmetries here, epsilon. And as you can see, for a washout of about 1000 and an CP symmetry of about 10 to the minus 3, we are right here in this blue band, which is the experimental value. So we are in the right spot to get the right asymmetry at the end of the day. So our model is very promising for that. And then just want to quickly mention that so remember that the Euclid couplings depends on the two parameters A and B, which are unconstrained or very hard to constrain experimentally. But just for the sake of it, we performed a scan just to make sure that there was no fine-tuning necessary in our model to get the right asymmetry at the end of the day. So here on the left-hand side, I show the value. So I varied the two values of A and B. And the contour plot shows the scale of leptogenesis, m squared over mu, that we need to get the right asymmetry, lepton asymmetry in the end. So for the normal hierarchy scenario, we need about a scale of 1 PeV. And on the right-hand side, it's the same plot, but for the inverted hierarchy. And in the inverted case, we need a slightly larger scale, so about 10 PeV. But for most of the parameter space, there's a scale where we achieve the right asymmetry. So it looks like our model does not need any fine-tuning in the end. But like I said, it's very hard to constrain these two parameters further because the Yukawa couplings itself is so small. So experimentally, there is not very bound that we can put on these two parameters at the moment. And that's it. I'm sorry it was a bit quick, but what I went to say essentially was that our model does achieve leptogenesis at the PeV scale. We needed to have two types of fields, so N and N prime, but they both play an important role in our model. So N, the heavy state N, is responsible for inducing the light neutrino masses, and then the light state N prime is responsible for leptogenesis itself. And we needed some resonant enhancement of the asymmetry to compensate for the large washout of the decays. So that was what I had to say. Are there any questions?
So I'm not sure if we want to have Jim do a final slide and then give some people more chance to ask questions, since no one's put their hand up immediately. I think Jim said he had a final slide to show.
Yeah, maybe you can show it, Jim.
Yeah. Yes, so whoops, just to wrap up. Yeah, so just to remind you of what we discussed, we gave an explicit construction of a PeV scale SUSY-breaking model that has a strong first order phase transition, and it's rather predictive. The scale is constrained to be not too far from 30 PeV, and it's a rather narrow window that could eventually be closed by say for future circular collider search for gluino. In this model, the dark matter is a gravitino, and its mass is also rather constrained to be within a few GeV. We can get observable gravitational waves for several upcoming experiments, possibly primordial black holes, but we need to do further investigation, like as Benoit mentioned, a simulation of the phase transition to quantify that. And I think we have a rather novel mechanism within supersymmetric models for generating neutrino mass and low-scale leptogenesis. So thank you very much for your attention.
Thanks to all three of you for the very nice talk, and I think it worked quite smoothly with the transitions. So now people can raise their hands and they can ask a question to any of the three speakers for any part. I also have questions, so if people are not fast to raise their hands, I think I'll start asking my questions and give them time to think. If you have problems with the raise hand feature, though, please do just unmute and ask, because sometimes people have problems with that feature. Okay, so I actually have a very naive question to start with, which is just, so you have the first order phase transition in the production of primordial black holes, and you also have the leptogenesis, but it wasn't clear to me how strongly they are linked. So do you always have both happening at the same time, or they're kind of completely independent, or?
Yeah, they're pretty much independent, because the leptogenesis part depends mainly on the Yukawa coupling that Jean-Samuel presented. So, and black hole production doesn't depend at all on that. So yeah, there's not a huge link between the two.
And not even with just the first order phase transition, right? Because the leptogenesis, the outer thermal equilibrium isn't coming from that, so it's.
We were we were hoping to find a link, because we were hoping that this mass gain mechanism would have something to do with the leptogenesis, and it didn't work out that way.
I see. Okay, thanks. Let's see if someone has raised their hand. Otherwise, I'll keep asking questions. I don't see it, so let me just ask another. So with the, I don't know much about this production of black holes, but I know that people also looked at quark nuggets and Fermi balls and Q balls. It's just a naive question on that is like, can you also get those things in the same model? And is it something that can happen in a similar scenario, or it's not possible?
Yeah, we haven't looked at that possibility, but I know, for example, for Fermi balls, you need to have some asymmetry present before the phase transition between matter and antimatter, simply because you want to have a remnant. So if you don't have that asymmetry, all the particles inside your anti-bubble will just annihilate completely and you won't have any remnant. So yeah, that's something that I don't think we necessarily have in our model right now. But yeah, maybe it's something that we could engineer to have that.
Okay, I see. So it is possible to have it in the model. Thanks.
Well, wait, what about the lepton asymmetry? Maybe that's not promising for
yeah,
further
depends on the
involvement.
temperature scale, because
Mhm.
we only generated at a lower scale, lower than the phase transition. So unless they decay, unless the transition is slow and then the entire bubble collapse after the neutrinos have decayed, but I don't think that's also, no, that doesn't work because before a phase transition, we don't have this mass splitting. Actually,
Yeah,
no,
right.
because there's no lepton violation when X doesn't have a valve. The only lepton number violation comes from the X valve. It's the lambda prime X
I see.
coupling.
So in
So
the
outside of the bubble,
anti-bubbles, we don't
there's
have any
no.
asymmetry.
That's right.
Okay.
That's right.
Okay, thanks very much. So also you showed, can you show the plot again where you had the points plotted on the gravitational wave curves plot? I think that was Benoit.
Oh yeah, I can show that.
So I thought I noticed the points are getting very close to LIGO actually, but somehow just missing it.
Yeah, they are really close, but yeah, that's a bit unfortunate. Yeah, I found no points in the LIGO region of sensitivity.
But it's sort of, you're getting fewer and fewer points as you're going higher up. And so it's not clear to me if maybe you could hit LIGO if you scanned more targeted there, or you're pretty sure you can.
Yeah, actually, these points come from that yellow region here on that plot. So it's a really small part of the parameter space.
Okay.
And I don't think there would be any more space like to scan more here. Yeah.
Okay, I see. Okay.
Because if we go lower, we just don't have any nucleation and no first order phase transition.
Okay. So in a sense, it's a shame that you don't get a constraint, but nonetheless, it's showing that it's just on the edge of detectability. So.
Yeah.
Interesting. Okay, so I just want to check. So let me give a little bit more time for people to just unmute and ask, because I'm hogging all the questions. So if you have a question, please just unmute and ask.
Yeah, so a question for Benoit. So I'm not an expert on the exact process I'm learning. I'm trying to learn about baryogenesis in general, electroweak baryogenesis in particular. But no, I think the idea of having these primordial black holes from this process is very creative. So I really like it. So I was wondering, how did you, like, I know that there are Sphaleron interactions, not just the weak Sphaleron ones, but also there are like SU3 Sphalerons interacting outside the bubbles. So I don't know how did you, or if you had to include these interactions when you computed like the amount of matter, thermal matter that will accumulate to finally allow you to get these black holes.
Yeah, no, we didn't have to take into account the Strong's tolerance, for example. Yeah, basically the only thing we're interested in is these particles that are reflected and are trapped inside the false vacuum. So we just assume that this number of particle is constant, essentially, in the entire bubble.
So you didn't calculate like the interactions with because yeah, like those non-perturbative solutions are still out there, right? Like they will be interact with the particles that are getting reflected from the bubbles, or like, yeah, I don't know. I was expecting that there will be some more interactions, perhaps, I don't know, annihilation or creation of particles, and I don't know, like the dynamics seem to be complex.
Yeah, of course that's something that can happen, and in a more realistic scenario this will lower the number of particles that you have in your antibubble. Here we just assume that these processes are slow, so that they don't play too much on the number of particles inside of it.
I see. And the other question regarding like that process is, I know when you compute the electroweak baryogenesis through the bubble, you use some approximations. For example, assuming that the bubble is big enough, then you can assume that the metric is flat. But for the anti-bubbles, I don't know if the same assumption will work. Like perhaps you should, or you probably could worry about the metric, the precise metric of the space for doing computations.
Yeah, here we assume a spherical antibubble, but actually we don't really care too much about the geometry of the bubble. We simply need to make sure that these particles inside the antibubble don't have enough kinetic energy to go through the wall. So if that's the case, they will always be reflected. So all that geometric dependent dynamics that can happen inside of the wall, we don't need to care about that. We just know that because of energy conservation, it's impossible for these particles to escape the bubble by going through the wall.
Yeah, I see. But I meant like the space-time geometry, because at the early universe, is the FLRW metric. So I don't know, maybe like the space-time cannot be assumed like as planar as when you take locally these calculations at the bubble walls.
Yeah, here we just take a flat space-time. So yeah.
Okay, I see. And one final comment regarding that, because I found it very interesting. So I always had an idea, but I never pursue it. And it's that, what about this matter that doesn't get through the bubbles? Like in your model, you are considering that it eventually forms black holes. What if it just stays there, like Fermat Relic, and is a dark matter candidate or something like that?
Yeah, that's the idea with Fermi balls, for example. So in the case where the thermal pressure is large enough to stop the collapse, that would form that kind of object that has been studied in other papers. But like I said, you need an initial asymmetry in the false vacuum to have a remnant. Otherwise, they would just annihilate completely if you wait long enough.
I see. Very interesting. Thank you.
Yeah, thank you.
Yes, thanks very much. So are there more questions? If you have a question, please unmute and ask. So I do have a few more questions. Maybe I'll just ask one more. Yeah, which one? Yeah, so the you commented about the signal to noise ratio greater than 10. Do you know how And you said that that's a rough criteria for discovery. Can you comment more on the things that go into that and the other possibilities? Or
I'm really not I'm not an expert about that part of the calculation, so I don't really know how they come up with with that number. I think they do some kind of simulation to kind of have an idea of what kind of signal they can expect. But I really cannot tell you more about that, unfortunately.
okay, that's okay. I also have some things I don't know about that, which is why I was asking.
Okay.
So sorry, let me just one more last thing. When you showed R in your gravitational wave fits, I think you called it the mean bubble size. Is it really the mean bubble size there, or was it the mean bubble separation? Do you know? Which one you were using? And
I think it's the mean bubble size, but I'm not completely sure. Usually I convert it in terms of the beta parameter.
Okay.
But I don't remember exactly. If I remember correctly, it's the mean bubble size, but
Okay, interesting.
I'm
Just normally the fits are to the mean bubble separation. The mean bubble size is it fits the relation to beta a bit better for longer, so it's not so temperature sensitive. But anyway, that's all. Okay, so let's just see if give anyone in the audience just one more chance to unmute for a very quick last question. Otherwise, I think we can close the session. Don't see anyone. Yeah, seems not to be the case. So thanks to all three of you for the really, really interesting talk. I really appreciated it, and I'm sure everyone else did as well. I did start recording the video a little bit into Jim's part. Sorry for that.
That's okay.
Yeah, I always used to forget when I was organizing these regularly. So it's happened before, and then I'm out of practice now, so it's even more likely to happen. But do you mind if we put the slides up with
no problem. I'll send them to you.
And also the video we'll put on our website. Is that okay?
Yeah.
Thanks a lot. Okay, so thanks very much again, and hopefully
Thank you, Peter.
see you again sometime. It'll be great. It would be great if one day some of you can come to China, or well, Benoit's been very recently, but good to see you here.
Okay, thanks very much, Peter.
Thanks. Bye.
Thanks a lot.
Bye-bye.
Bye.
Bye-bye.